Let us put it into practice. The seed is this number here. It can start from 0 and go up to a very large number, so each seed can produce a slightly different result. If you also change the prompt and settings, you can get millions of different results. We can control the seed behavior. If we set it to fixed, we generate once and the result will never change. To generate something new, we need to change other settings. If we choose increment, after each generation the seed number will increase by 1. If we choose decrement, after each generation the seed number will decrease by 1. So let us change it to fixed and set the seed to 10. When I generate, I get this robot. Now let us change the seed to 15. You can see that I get a different robot, this time in profile. If I change the seed back to 10, I get the previous robot again because we used the same prompt, the same settings, and the same seed. In prompts, the order of the words matters. With this prompt, I got this image because house was first. So the model focused on the house and mostly ignored the car. With newer models, this happens less often, but this is an older model, so the effect is more noticeable. Now look at what happens if I put car first, and then house. This time we clearly get both a car and a house. Words that appear earlier in the prompt usually have more influence than words that come later. You can think of the prompt as a list of priorities. The model pays more attention to the beginning and gradually less attention as it moves toward the end. On top of that, some words can carry more weight, either because of how the model was trained or because we explicitly give them extra emphasis. Because of this, two prompts with the same words, but in a different order, can produce noticeably different results. Think of the prompt like giving directions to someone. If you say, a red cat sitting on a chair in a room with soft lighting. The most important idea is red cat. Everything after that adds detail, but the core idea comes first. We can also add more weight to a word by using round brackets. Right now, house has more weight, so the model pushes the car into the background and it is no longer the main focus. If I add even more brackets, the influence of house becomes even stronger, and now the car disappears completely. If I instead add more weight to the word blue, you will see more blue appear in the generation. One more thing you might notice is that there is no spell check by default. Sometimes it can be useful to turn it on. To do that, go to Settings, search for Spell, and enable Text Area Widget Spell Check. Now, words that are misspelled or not part of the dictionary will be underlined. Now we talk about denoising steps. Steps control how many refinement passes the model performs during generation. Each step removes a small amount of noise. The image is not created in one action. It is refined little by little, step by step. When you increase the number of steps, the model has more chances to clean up noise and add detail. When you decrease the number of steps, the process is faster, but the image can look rough or incomplete. More steps means slower generation and more refinement. Fewer steps means faster generation and less refinement. There is always a balance between speed and quality. You can think of steps like polishing an object. More polishing gives a smoother result. Less polishing is faster but rougher. In ComfyUI, steps are set inside the K-sampler node. For most models, a good starting range is between 20 and 30 steps. Going much higher often gives diminishing returns. Going much lower is useful for fast previews. Steps work together with the seed and the prompt. The seed decides the starting noise. The prompt guides the direction. Steps decide how far the refinement goes. Now we are ready to look at a real workflow in ComfyUI. This is called text-to-image, often shortened to text-to-img. Text-to-image means we start from pure noise and generate an image only from text instructions. There is no input image involved. This is usually the first workflow people learn, and it is the best way to explore ideas and styles from scratch. We start by loading a model. This model contains everything the AI learned during training. Next, we give the model instructions using a text prompt. This describes what we want to see in the image. We also define the image size using an empty latent image. This decides the resolution before the image is generated. Then, the K-sampler runs the diffusion process. This is where noise is removed step by step, guided by the prompt. After that, the VAE decodes the latent result into a visible image. Finally, the image is saved to disk. Use text-to-image when you want to explore new ideas, you want to test prompts and styles, or you are starting from nothing. This workflow is ideal for concept art and experimentation. But we can also start from an image, not just from pure noise. In that case, instead of beginning with random noise, we use an existing image as the starting point and apply denoise on top of it. You can think of denoise as how much freedom the model has to change the image. With low denoise, the model stays very close to the original image. With higher denoise, it moves further away and behaves more like text-to-image. So rather than generating everything from scratch, we are guiding the diffusion process using an image as the base, and then controlling how much it changes using the denoise value. Image to image is like starting with a rough sketch and deciding how much you want to redraw it. You can see that in the text-to-image workflow, we have empty latent image. That node generates the noise. In this workflow, we have an image that is encoded to latent so it can go to the K-sampler. Let me show you how I did it. I removed the empty latent image node, then I double-clicked on the canvas and added a load image node. From here, we can load an image, and I will choose this robot. Now you can see it does not have a latent output, so we cannot connect it to the K-sampler yet. So we need a VAE. If we look, we have decode and encode. We already have VAE decode when it converts from latent to pixels. Now we want to encode it. An easy way to find the right node is to drag a link and release it, and you will see a suggestion for VAE encode. Now we have a latent output, which means we can connect it to the K-sampler, which is what we want. If we try to run it like this, something is missing. It says, missing VAE. You can see a big red outline around the node with the problem, and a small circle around the input, which means we need a connection there. So let us connect it to the VAE. In this case, the VAE is included in the main model, so we connect it from there. Now we encoded it, and then we decode it. Let us run again, and now it works. But the result is still different from my input. We have the right prompt, but something is influencing it. Remember this. Every time you use an image as input, we need to adjust the denoise, because that controls how much the image changes. With the default value of 1, it is at the maximum, so it changes the image too much. Let us change it to 0.2 and see how that affects it. Now you can see it is very similar to the original. It is hard to tell what parts changed. Let us increase it to 0.5. Now we can see more changes in the robot face. There is an easy way to compare these images. Double-click on the canvas and search for Image Comparer. This is part of the RG3 node pack. You can see it has two inputs, image A and image B. I want to compare the original image, so I will connect the load image output to image A. For the second image, remember the Save Image node is only for saving to disk. The image we want to compare is the one coming out of VAE decode, so we connect that to image B. Now let us run the workflow. We get this small preview. Let me make it larger. It is still too small, so I will move some nodes to make space so you can see it better. By default, it shows image A, the original. When we move the mouse over to the right, it shows the second image. Now it is much easier to compare before and after. If I change denoise to 0.1, we get a very similar result, because the amount of denoise is small. If I change it to 0.9, we get a big variation. All of this is also influenced by the sampler, the scheduler, and the model itself. But in general, this is how it works. I prefer to start with values around 0.7. If that is too much, I reduce to 0.5 and keep adjusting until I like the result. Another thing you should know is that the input image size influences the result size. Since we do not have an empty latent image node where we set width and height, the loaded image decides the size. ComfyUI will also round the size to a multiple of 8. For example, if your image is 511 pixels, it can be rounded down to the next number that is a multiple of 8, like 504. You can also control the input size by resizing or cropping it, like you saw in the earlier chapters. For example, I can add an upscale image node here, then redo the connections so the image passes through it. I can upscale to a bigger size with the same ratio. Now when I run it, the final image should be larger, because it follows the input image size. Now we are going to talk about samplers and schedulers, which you can find here in the K-sampler. This is one of the most confusing parts at first, but the idea is actually simple. Everything begins with the same initial noise. The seed defines that noise, but once the noise exists, two different systems control what happens next. The sampler decides how noise is removed. It defines the strategy the model uses to go from noisy to clean. Different samplers use different mathematical paths to denoise. Some remove noise more directly. Some refine the image gradually. Some are more random and creative. Some are more stable and precise. Even with the same prompt, the same seed, and the same number of steps, changing the sampler can change the final image. So the key idea is this. Sampler controls how each denoising step is calculated. Or in simple terms, sampler equals how noise is removed. The scheduler does not change how denoising works. It changes when denoising happens during the steps. A linear scheduler spreads denoising evenly across all steps. Each step removes roughly the same amount of noise. A nonlinear scheduler removes noise faster at the beginning and slower near the end. This allows fast structure early and fine detail later. Both approaches can reach a clean image, but they feel different in how detail is introduced. So the key idea here is scheduler controls when noise is removed. Or simply, scheduler equals when noise is removed. Sampler and scheduler always work together. You never choose one without the other. The sampler chooses the denoising method. The scheduler chooses the timing of that denoising. The same noise, plus a different sampler or a different scheduler, can produce different results. Let us do a little experiment in ComfyUI. From Workflows, I open again this text to Image Workflow, and I change the seed to Fixed. Then I run the workflow. With this sampler and scheduler, we get this robot. Here we have a lot of samplers and schedulers. Depending on the model we use, some work better than others. Let us say I pick the Euler sampler. Now when I run it, even if the seed and prompt are the same, the result is slightly different, because the sampler influences how the denoise is applied. Let us say I also change the scheduler to simple. Now the result will again be different, because the scheduler changes when the denoise happens during the steps. Because the model we use is quite small, we can actually preview multiple results at the same time. So I hold the Control key and drag over these three nodes. Then I use Control plus C to copy them, and Control plus Shift plus V to paste them with the links connected. Now this workflow will generate two images and has two K-sampler nodes. Let me use Control plus Shift plus V again to get a third one. Now this workflow uses the same seed and prompt with three different K-sampler nodes, and I want to change the samplers and schedulers for each one. You can play with these all day and try many combinations. I will choose something random for this example. Now when I run it, you can see it generates an image for each sampler. Some results are quite similar, but some details are different. For example, parts of the robot may change from one image to another. Let me now put the same sampler on all of them and use different schedulers only, so we can see how the timing of denoise influences the result. Again, the differences are subtle, but they are there. Sometimes this can mean one image has 5 fingers and another has 6, so having options is useful, especially when you want small variations. Now let us double-click on the canvas and add a primitive node. I want to control the steps value for all 3 K-samplers, but I do not want to change it manually on each one. So I drag a connection from the primitive node to the steps input of the first K-sampler, then do the same for the second and the third one. Now from this single node, I can control all 3. If I change steps to 1, you can see we get very similar results. If I change steps to 3, you can already see differences. Some schedulers are faster. For example, with one scheduler, the image is still very noisy, while with another, you can already see a shape forming. If I change to 4 steps, the differences become more visible. At 5 steps, some start to form clearer shapes. At 6 steps, some images already show eyes and a main structure. At 8 steps, the middle one is almost fully formed. At 10 steps, almost all of them have something that could work for certain concepts. And at 20 steps, most of them have enough detail to be usable in a project. Usually, the people who create AI models suggest specific samplers and schedulers, or the community tests them and shares which ones work best. This way, you do not have to test everything yourself for every model, but if you do find good settings, it is always a good idea to share them with the community so everyone can improve their image generation results. Let's talk a little about subgraphs. In ComfyUI, go to Workflows and open the Juggernaut text-to-image workflow. Here you can see a bunch of nodes, just like before. Hold the Control key and drag to select most of the nodes, except the Export node, which in this case is the Save Image node. Now that the nodes are selected, look at the icons at the top. One of them says Convert Selection to Subgraph when you hover over it. When you click it, all those selected nodes are combined into a single node. If you right-click on this new node, you will see an option called Unpack Subgraph. When you click it, the nodes go back to how they were before. Let's do it again. Select 2 or more nodes, then use the Subgraph button to create a subgraph. Resize it so it is easier to see. A subgraph is a way to group multiple nodes into a single reusable block. Instead of showing a long chain of nodes every time, you collapse them into one node that represents an entire process. You can think of a subgraph like a function or a macro. Inside it, there can be many nodes, but from the outside, it looks simple. It is very similar to smart objects in Photoshop, which can contain multiple layers inside a single object. Subgraphs solve 3 main problems. First, they reduce visual clutter. Large workflows can become messy very quickly, and subgraphs help keep things readable. Second, they help reuse logic. If you repeat the same setup many times, like a prompt encoding chain or an image preprocessing step, you can reuse it instead of rebuilding it every time. Third, they make workflows easier to explain and share. People understand a few clean blocks much faster than dozens of individual nodes. At the time I recorded this tutorial, subgraphs were still being improved and may still have some bugs. A subgraph does not make a workflow faster by itself. It is about organization, not performance. Performance depends on the nodes inside the subgraph, not on the subgraph wrapper. A subgraph is like putting many Lego pieces into one box and labeling the box with what it does. All the pieces are still there, you just do not need to see them all the time. You can see the title says New Subgraph. Let's double-click on that and rename it to something that makes sense, like text to image, and maybe also include the model name. So Juggernaut text to image. Now it looks like a simple workflow with only 2 nodes. I do not like the order in which things appear in the node, so let's right-click on the node and select Edit Subgraph Widgets. Here you can choose what parameters to show in that node and what to hide. Let me hide all of them so we have a clean subgraph that does not show any parameters. You can enable them one by one later if you want only the ones you need, but we will build those manually so you understand them better. Let's close this panel. Now let's go inside the subgraph. You can see that all the nodes are there, plus some input and output. On top, you can see a new tab next to the workflow name. If I click on the main workflow name, that is how we exit the subgraph. From there, we can go back inside, and from inside, we can go back outside. You can see the output where the image is saved. If we go inside the subgraph, that image output appears here as a link. From this dot, we can drag a connection to where it says checkpoint name. Now that field becomes gray, just like when we added a primitive node before. If we go back outside, you can see that the checkpoint name appears here. Let's go back inside again, double-click on that name, and rename it to model to see what happens. Now when we go back to the main workflow, You can see it says model instead of checkpoint name. So this is very customizable. Let's go back inside and drag another connection, this time to the positive prompt, and rename it so we know what it is. Do the same for the negative prompt. Now when we go back outside, we have positive and negative prompt visible. Go back inside again and drag connections to width and height, and maybe do the same for all the parameters from the K-sampler. Now we can see all those parameters exposed here, and when we go back outside, we have this single node that acts like a mini interface that can control everything we need. You might say that it looks nice, but does it actually work? Let's try it. And the answer is yes, it works. If you right-click on it, you can see it still has other options, like node color, bypass, and so on. With that subgraph selected, right-click on the canvas this time, and you will see an option called Save Selected as Template. It asks for a name. I will name it Juggernaut Text to Image, then press Enter or Confirm. It looks like nothing happened, but where was that template saved? Let's open a new workflow. Now right-click on the canvas and go to Node Templates. You can see that name there now, and you also have the option to manage templates and remove them. When I select that template, it is added to the canvas with all the nodes, connections, and settings it has inside. Now we can just drag a link from the image output and add a Save Image node, or connect it to other nodes to create more complex workflows. Over time, this simplifies workflows because we can organize them into pieces and group them by category or function. Let's go back to the first workflow, just to show you that any node or combination of nodes can be saved as templates. There are cases where some connections can break when some nodes are inside a subgraph and others are outside, so keep that in mind. For example, I use this Pixaroma note node a lot. I want to save it as a template so I can access it easily next time. This might not be useful for everyone, but as a workflow and tutorial creator, I use this a lot. I will save it as a template and give it a name. Now I can go to any other workflow and quickly access that template from anywhere. You can also have subgraphs inside other subgraphs, like boxes inside boxes. You can disconnect or remove links at any time. I could select two nodes here and combine them into another subgraph, or go outside and combine all these nodes, even if some are simple nodes and one is already a subgraph, and it will still let me create a new subgraph. If we go inside, all those nodes are there. If we go back outside, we can unpack it using the icon, or right-click and choose Unpack Subgraph. These things will make more sense as you work with them in practice, so play with them and have fun. When you see that icon on a node, you know it is a subgraph. It also has the icon that lets you go inside the subgraph, which is another indicator that it is not a simple node. Remember that you can also use the interface to edit subgraph widgets. One thing I forgot to show is that you can use those dots to rearrange the order of the parameters shown in the subgraph node. This way, you do not need to go inside it most of the time. You can control things directly from the outside. Now we are going to talk about LoRaS. LoRa stands for Low Rank Adaptation. In simple terms, a LoRa is a small add-on that modifies how a base model behaves. A LoRa does not replace the model. It works together with the model. You can think of the base model as the main photographer we hired earlier. A LoRa is like giving that photographer extra experience in a specific style or subject. Why LoRaS exist? Training a full model is very expensive. It requires a lot of images, time, and powerful hardware. LoRaS exists to solve this problem. Instead of retraining a full model, we train a small adapter that teaches the model something new. This could be a specific art style, a character, a face, a pose style, or a lighting style. LoRaS are much smaller than full models. That is why they are easy to download and experiment with.